Next, we will discuss the critical value approach to determine when a test statistic is too far from its expected value, defined by the null hypothesis. In the critical value approach, too far is defined by the range of values called the rejection region. If a statistic falls into the rejection region, then it is interpreted as a strong evidence against the null hypothesis in favor of the considered alternative. We draw the region according to the type of the test. For the demonstration purposes, we use a generic probability density curve of some distribution x. But in an actual application, it can be z, t, chi-square, or f, depending on the procedure. It should be easy to see the association between the type of the test and the way the rejection region is drawn. Also, the area of the region must be equal to alpha. By having the area of the rejection region equal to alpha, we guarantee that the probability of type 1 error is not greater than a preset significance level. Geometrically, the rejection region is defined by its boundaries, which we call the critical values. For a right-tail test, the rejection region is the right tail with the total area alpha, so it is defined by only the right critical value, which can be expressed as x alpha. For a left-tail test, the rejection region is the left tail with the total area alpha, so it is defined by only the left critical value, which can be expressed as x 1 minus alpha. For a two-tailed test, the rejection region with the total area alpha is split evenly between the left and the right tail, so there are two critical values, the left and the right, x 1 minus alpha over 2 and x alpha over 2. In the critical value approach, the decision whether to reject the null hypothesis or not is made based on whether the test statistic is in the rejection region or not. We just discussed the critical value approach, which utilizes the idea of a rejection region to determine whether the test statistic is too far from the expected value.